Okay. Yeah. So once again, good evening, everyone. So my screen is visible to everyone.
Yes, sir. It's
Okay.
visible.
Okay. So today we have a 11th class. Okay, and still we are in the third unit, and that is the most important unit for the electrical drives. Okay, so we can set the modeling and control of the electric drives. Okay. So in the previous class, we discussed the single phase half control of the DC motor and three phase fully control rectifier of the DC motor. Correct. So in the previous class, last class, we discussed these two topics. Okay. So today we will cover the starting with the three phase half control. Okay, so we already discussed the three phase full control as well as the single phase half control. So similarly, we have a three phase half control rectifier. Okay, then there is a reverse motoring. So we can see the DC motor reverse switching diagram. Okay, how we can how we can rotate the motor in reverse direction. Okay, then we will discuss the dual converter control of DC separately excited motor. Okay, so basically there is a dual converter. Okay, so we have to connect the both converter. So both are connected in the anti-parallel. Okay, and then drawbacks of the rectifier. Okay, so suppose we are using the rectifier circuit for the controlling of the DC motor. So what are the drawbacks? Okay, then finally we will discuss the chopper control separately excited DC motor. Okay, so we all know about the chopper, correct? So chopper is nothing but DC to DC converter. Okay, so still now we discuss the rectifier, that is a AC to DC converter. Okay, and then we will see the drawbacks of the rectifier. That's why we have to propose the new control algorithm, that is a chopper control for the separately excited DC motor. Okay, so these are the flow of the today's class. Okay, so starting with the three phase half control rectifier. So three phase half control means we have a three thyristor and we have a three diodes. Okay, then we can say it is a three phase half control rectifier. So you can see we have a circuit something like that. Okay, so we have a diode, we have a switch, we have a switch, and we have a diode, and here we have a motor. So we can say RA, LA, and E, and here we have a DC supply. So we can say T1, T2, T3, and we can say D1, D2, and D3. So we have a three thyristor. Okay, so we can say T1, T2, and T3. We have a three thyristor switches, and we have a three uncontrollable semiconductor switches. That is nothing but diode D1, D2, and D3. So by combination of the diode, so we can say the combination of the controllable switch and uncontrollable switch, we can make three phase half control rectifier. Okay, so you can see this circuit. Okay, so we have a AC supply. Okay, AC source. Okay, so we have a three phase supply. So here is a three phase. So yes, so this is a three phase. So we can say this supply. Okay, three phase AC. Yeah. So we have a three-phase AC supply. Okay, we can set R, Y, and B. We have a switch. There is a controllable switch. So these are the controllable switch. So we can set the controllable switch. And we have a uncontrolled switch. Uncontrolled switch. And this is your motor. We can set a DC motor. So we already seen the waveform and quadrant operation of the three-phase fully controlled, correct? So three-phase fully controlled motor operate in the two quadrant, and three-phase half control motor operate in the single quadrant. So we already know three-phase fully controlled DC motor operate in the two quadrant. There is a first and fourth. Okay, but three-phase half control rectifier is operate only in the single mode. We can say the single quadrant. So there is a forward motoring mode. Okay, so this is a forward motoring mode. And why operate only on the single quadrant? Because of the we have a three thyristor and we have a three switch. So that's why it is operate in the single quadrant instead of the three quadrant. Okay. Yeah, so we can write the simple equation similar to the three-phase circuit. Okay, for the rectifier circuit as shown in figure 1, so there is a input is a AC source and output is a DC, and DC output that is directly feed to our DC motor, and DC motor is separately excited DC motor, otherwise the shunt DC motor. So under the continuous conduction mode, we already discussed there are the two mode, maybe the single phase or three phase, half or full. We have a two mode, there is a continuous conduction mode and discontinuous conduction mode. For the continuous conduction mode, we can say output of the three phase half control rectifier, there is a VA equal to 3 Vm upon 2 pi into 1 plus cos alpha, and alpha is nothing but your firing angle for the three thyristor. Okay, so we can say we will get the output voltage here output voltage that is a 3 Vm upon 2 pi plus not plus into 1 plus cos alpha. Okay, so that is the first equation. So how much voltage we will get? There is a 3 Vm upon 2 pi 1 plus cos alpha. Okay, from the fundamental drive equation, we already discussed the fundamental drive equation. Okay, so from the fundamental drive equation, we have a value of a VA. Okay, so we can set the VA plus IARA plus LDIA by dt plus omega m is equal to 0. From this equation, we can write next equation, there is equation number 2. Yeah, so that is equation number 2. So that is a fundamental equation. Okay, so we can say the omega m. Suppose you want to control the speed of the DC motor by the rectifier circuit, and that is a three-phase half control rectifier circuit. So that omega m that depend on the Vm, that is a maximum voltage, firing angle, armature resistor, torque, and the constant value. So we have to control these 5 parameters. So suppose you want to control the speed. Okay, so that speed equation is a 3 Vm upon 2 pi k into 1 plus cos alpha minus Ra upon k square into t. And this equation we can derive by the fundamental equation, correct? So we already know Va is directly proportional to the speed. Otherwise, we can say the omega m. Torque is directly proportional to the flux into current. And suppose you remove the proportionality, so we can say torque equal to K into phi into I, correct? And using this equation, we can derive this equation. Okay, so that is omega m equal to 3 Vm upon 2 pi k into 1 plus cos alpha minus Ra upon k square into t. correct? So there is a important equation is first and second, okay? And you can see there is a VI characteristic. So on the y-axis there is a voltage, armature voltage, and on the x-axis there is a armature current. So motor is operate always in the first quadrant, and whenever we can say the first quadrant, it means that is your forward motoring operation. But three-phase fully control is operate in the first as well as the fourth quadrant operation. Okay, so now that is a next topic, that is the DC motor reversing switch diagram. Okay, so for the single phase fully as well as the three phase fully control rectifier for the DC motor is most important. Okay, half control is a little bit, we can say it is a not normally we use in the practical application, because that is only operate in the first quadrant operation, correct? So normally we use the single phase fully control as well as the single phase three phase fully control rectifier to control the DC motor. Okay, now we have to study the DC motor reversing switch diagram. Reversing switch diagram means suppose your motor is operating in the clockwise direction. So now you have to operate in the anti-clockwise direction, correct? So how we can operate this switch? How we can operate this motor in the clockwise to anti-clockwise direction? Okay. So you can see the figure 1. 4 quadrant drives employee, single converter, and reversing the switch. Okay, so single converter is what? So this is a converter. Okay, so there is a thyristor based converter. We have a three-phase supply, 50 hertz. Okay, and we have a converter. Okay, so we will get the output voltage, and that output voltage we can give. This is nothing but VA, and we can give this VA to the motor voltage, that is armature voltage. Okay, so we can see this is a R and this is a. So R and S is nothing but your switch. Okay, so R and S is nothing but the switch. Okay, so DC motor reversing switch diagram is shown in figure 1. Yes, simple diagram. So we can say this is an inverter circuit and this is your motor. Okay, a fully controlled rectifier feed the motor. Fully controlled rectifier feeds the motor through the reversing switch, that is a RS. Okay, so by switching of the RS, R and S, we can change the direction. Suppose here direction is a plus and minus. So by using this switch R and S, we can convert the direction, that is a minus and plus. Okay, so which is used to reverse the armature connection with respect to the rectifier. Okay, so suppose, just 1 minute, I am taking the different color. Yeah, suppose inverter direction is a positive and negative. Okay, and suppose motor direction also positive and negative, then motor is rotating in the clockwise direction. So we can say the clockwise direction. Okay, and suppose you want to change the direction from the forward to reverse, then what we have to do? So inverter direction is same, there is a positive and negative, there is a not issue. But now what we have to change the direction of the motor terminal. So by changing the direction of the R, so now we can say the positive, that is inverter, so we can say the R, there is a negative, and S, there is a positive. So now your motor is operating in the anti-clockwise direction. Okay, now your motor is running in the anti-clockwise direction. So we have to just change the terminal of the motor, otherwise the terminal of your inverter. Then we can able to rotate the motor in the forward direction as well as the reverse direction. Okay, a fully controlled rectifier is capable of the providing the operation in the quadrant 1 and 4. Correct, so that is maybe the forward motoring, maybe the reverse motoring. Okay, the reversal of the armature connection provide the operation in quadrant 3rd and 4th. Okay, So we can say, suppose that is a positive and negative, and there is a three-phase fully controlled. So we already studied. So single phase, otherwise three-phase fully controlled rectifier operate in the first quadrant as well as the fourth quadrant. Okay, but now you have a three-phase converter, and now you are changing the direction. Then we can say, now by using this circuit, we can operate in the second quadrant as well as the third quadrant. Okay, so we can say, suppose this is a V, suppose this is a IA, and this is a VA. So we can say this is a forward motoring, forward braking, reverse motoring, and reverse braking. Okay, so by positive direction we can operate first and fourth quadrant, and then reverse direction we can operate the second and third quadrant operation. Correct? So by just changing the direction, by changing the terminal of the motor, we can operate our drives in the all quadrant, that is a four quadrant. Okay, the DC motor reversing switch diagram may consist of the relay. Okay, so relay is nothing but your switch, correct? We have to use the relay to just operate the switch, correct? So relay is nothing but it is a switch. Relay operated contactor with to normally open and to normally close the contact as shown in figure 2. So you can see this is a forward and this is a reverse. Okay, so this means it is a open terminal, and this reverse means closed terminal. So it is up to you. You want to operate your motor into forward direction, yeah, reverse direction. Okay. So suppose this one is open, then we can say the current is flowing from this direction to this direction. Okay, and this to this, and again feed to the, here is your converter. Correct? So circuit is completed. Correct? And suppose you want to rotate in the forward direction, then we can say we have to operate this one, this to this. Okay, correct? And yeah, this to this, correct, and this to this, and like this. So we can say like here, 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 and here, and return. Okay, so we can say, so based on this relay operation, we can operate the our motor in the both direction, that is a forward as well as the motoring mode. Okay, yeah, that is similar to instead of the simple relay, we can also use the our thyristor. Okay, so thyristor is a forward as well as a thyristor for the reverse. Okay, so based on your operation, we can operate the thyristor, that is a forward direction as well as the reverse direction. Okay, so when slow operation and the frequently maintenance associated with the contractor is not acceptable, reversing the switch, it is realized using the fourth thyristor is shown in the figure 3. Suppose sometime your contact, otherwise relay contact is not possible, then we have to use the power semiconductor switch to operate our motor in the fourth quadrant. Okay, with the thyristor pair TF is on and pair TR, that is off. As we discussed in the previous slide, there is a F and there is a R. So hence F, that is a open terminal, and R, that is a closed terminal. So one by one we can operate in the open terminal as well as closed terminal. Suppose you want to operate motor in the forward as well as the reverse direction. Correct? So same concept we have to apply for the thyristor. Okay. So thyristor is nothing but simple switch, and we can say the relay is nothing but the simple switch. Okay. So with the thyristor pair, there is a TF on and pair TR is off. Operation is obtained in the quadrant 1 and 4. Okay. And with the pair of TR is on and pair of TF is off, then operation is provided the quadrant 2nd and quadrant 4th. Okay. That is a similar to the previous one. In the both the configuration of the RS, the switch is done at the zero current in order to avoid the voltage spikes to reduce the etc rating. Okay, so main use of the this thyristor, so we can say we can reduce the voltage spikes. Okay, so we can ultimately reduce the current ripple, so we can ultimately increase the efficiency. Okay, so that's why we have to use the thyristor instead of the relay switch. Okay. Yeah, so this is a simple explanation of that diagram. The speed reversal transfer of the operation from the quadrant 1 to quadrant 3 or from the quadrant 3 to quadrant 1 is done by following step. Okay, so suppose you want to change your direction, maybe the quadrant 1 to the quadrant 3, otherwise maybe the quadrant 2 to quadrant 3. Okay, yeah, maybe the any quadrant. Okay, so how we can change? The firing angle of the rectifier is set at the highest value. So we have to set the firing angle because we have a thyristor. Okay. So we can operate the thyristor by firing angle. So we have to set the firing angle that is the highest value. Okay. Highest value. It work as a inverter and reduce the armature current to the zero. Okay. After the zero current is sensed, the firing pulse are the stopped. Okay. If the zero current firing pulses are stopped. Okay, a delay time of 2 to 10 milliseconds, so you can change this delay time, that is up to you, and that is your up to your control algorithm. Okay, but firing angle, that delay time, it is important to operate the one switch to another switch. Suppose we have a total 6 switch and you have to operate the all 6 switch one by one, so we have to put the delay time. Okay, so that is a 2 to 10 millisecond. It normally is provided to ensure that thyristor conductor have all the fully turned off. So this is a normally we can put there is a 2 to 10 millisecond, but you can also reduce this time duration and also you can increase this time duration depend on the switching frequency, depend on the clock frequency. Okay, so there is a time duration and delay time duration, that is depend on the many parameter. Okay, such a long delay compared to the thyristor turn off time, which is of few hundred microsecond, is required in order to take care of the error, that is a zero current sense. Okay, so zero current sense is what? So suppose you operate the firing pulse is here and then is again stop at time period here, so we have to give the some delay time and then we have to operate. So this delay time we have to, then we can say we have to operate. Okay, so something like that, that is your current, correct? So we have to give the firing pulses with the delay, okay, to operate the another switch. The current control adjusts the firing angle continuously so as to break the motor at the maximum allowable current from initial speed to the zero speed and then accelerate the motor again the maximum allowable current. Okay, so suppose you accelerate your motor, so accelerate the motor, it means we have to give the more current. Okay, and suppose you increase the speed, so we have to give the more voltage. Okay, so that depend on the direction of the motor and depend on the speed of the motor. Okay, the operation at the maximum current during the speed reversal ensure the braking and acceleration at the maximum motor torque to ensure the fast reversal. Okay, so suppose you doing this type of experiment, there is a forward motoring, reverse motoring, forward braking, reverse motoring. So we have to ensure that is a current is a minimum as well as the voltage is minimum and it will take minimum time duration. Okay, suppose it will take the large time duration, then it will create the ripple value. Okay, and nobody want to use the ripple with ripple the application. Okay, suppose there is a ripple in the motor, that it will create the less efficiency. Okay, yeah, so this is the DC motor reversing. So how we can reverse the DC motor by connecting the by connecting the two switch, that is maybe the reverse switch and forward switch. Maybe the you can connect the relay switch. Okay, otherwise maybe you can connect the fourth thyristor switch and then we have to operate the one by one. So by using this concept we can do the reverse operation of the our motor. Okay, yeah, so now we can discuss the dual converter. Okay, dual converter control of the DC separately excited DC motor. Any idea about the dual converter? What is the meaning of the dual converter? Yes, Archana, are you there?
Yes, sir.
Yeah, any idea? Previously you heard about the dual converter? What is dual converter? Maybe the first
I
semester,
don't
yeah,
know.
maybe the during BTech. Yes, no idea.
No idea, sir.
Okay. What about Isa Tiwari? Isa, are you there?
Yes, sir.
Any idea? What about the dual converter?
It means I think it consists of two converters, positive
Mm-hmm.
one set of positive converter and another set of negative.
Okay,
No,
so
I
80% is the
don't know
correct
much
answer.
about
So we
it.
have a two converter, one is a positive and one is a negative. So this positive and negative is a little bit wrong answer. But positive, we have a two converter, that is a correct. Yes, any other student? Yeah, what about Narayana, are you there?
Yes, sir.
So would you like to add anything? So Isa Tiwari said so dual converter means that is a dual converter. So we have a two converter. One is a positive, another one is a negative. So that answer is
Mm,
80% answer is correct. So we have a two converters. But would you like to add something? So that remaining 20%,
mm, it operates in all four quadrant.
that is a
Also,
correct.
uh, and it convert AC to DC or DC to AC or DC to DC or AC to AC. That type of converter, dual converter.
Okay. Yeah. Yes, Madhusudan, any idea?
Yes, sir. There are two converters
Mhm.
in which are connected in anti-parallel.
Okay.
Uh, one for the one direction and another converter for the controlling of
Yeah,
both.
so that is a correct. So we can say that we have a two converter. Okay. So both converter are connected to anti-parallel. Okay. So that is the dual converter. So we can operate our motor in the four quadrant. So that is the of the main benefit of the dual converter. Okay. So you can see this figure. Just 1 minute. Yeah, who want to join now after 1 hour? Niroj. Niroj, why you are too late? Okay, so you can see this diagram. There is a figure number 3, dual converter of DC separately excited motor. Yes, so we can say this is a separately excited DC motor. Okay, A and B are the fully controlled rectifier. So we can say the converter A, converter A, and converter number B. Okay, so we have a two converter. Okay, so converter A and B. In both converter, you can see there is an anti-parallel connected. So you can see here is a positive and here is a negative. But second one is a just reverse. There is a negative and positive. Correct? So we have a two converter and all are the fully controlled. Maybe the single phase, yeah, maybe the three phase, depend on the power rating. Okay. So currently we have a three phase fully controlled rectifier. Okay. And suppose your DC motor rating is a very low, then we can also use that is a single phase fully controlled rectifier, otherwise the three phase fully controlled rectifier. So that depend on the your motor power rating. Okay. And what about the L1 and L2? Okay. So L1 and L2 are used with the simultaneously control. Okay. Otherwise, you can say the continuous control. Okay. So L1 and L2 we have to use for the continuous conversion mode. Okay. So these are the simple diagram of the dual converter. Yes, student, we have to remember we have a two converter, converter number 1, converter number 2. Both converters are connected the anti-parallel to each other. In between, there is a motor is connected. There is a parallel with the both converter. Okay, so you can see this motor, DC motor is connected parallel with inductor L1 and L2. And what is the use of this inductor? To use of this inductor to control the, we can say the circulation of the current, not the control. Maybe we can say the circulation of current. And we already seen there is a continuous conduction mode. Continuous conduction mode. And second one is the discontinuous conduction mode. Okay. So by using the L1 and L2, we can operate that is a continuous conduction mode as well as the discontinuous conduction mode. Okay. So figure 1 show the dual converter control of the DC separately excited motor consists of the two fully controlled rectifiers connected in the anti-parallel across the armature. Okay. So there is a simple definition of the dual converter. Okay. And why we have to use the dual converter? So we can operate our motor in the 4 quadrant. So this is a IA and this is a VA. So this is a forward motoring, forward braking, reverse motoring, and reverse braking. So by using the 4 quadrant operation, by using the dual converter control operation, we can operate our DC motor in the all the quadrant. Okay. So now we can see the for the power rating up to the 10 kilowatt single phase fully controlled rectifier can be used. As I said in the previous slide, we can use the single phase fully control as well as the three phase fully control. Okay, but we cannot operate the single phase half control as well as a single phase three phase half control. Always we have to use the fully controlled rectifier to become the dual converter. Okay. For the higher power rating, we have to use the three-phase fully controlled rectifier. Okay, because it is we have to play with the higher power, then we have to use the three-phase. Okay. Rectifier A, which provide the positive motor current and voltage in either direction, allow the motor current in the quadrant first and fourth. Okay, so there is your first quadrant, that is we can say this converter 1, that is the first converter. Okay, so it operate in the first and fourth quadrant. Okay, and the rectifier B, there is a converter B, provides the motor control in quadrant second and third, because of it is a negative motor current. Okay, and that's why there is a third and second mode, that is your negative. Okay, so we can say your rectifier A is operating in the positive and rectifier B, that is operating in the negative. Okay, so there are two modes. Okay, as we discussed in the single phase as well as the three phase conduction mode, we can operate our converter in the circulation conduction mode as well as the non-circulation conduction mode. Okay, so circulation conduction mode, it means that current is not going to zero. Okay, so circulation means your current is continuously follow, it is not reached to zero. Okay, so we can say this is a IA. Okay, but what about the discontinuous conduction mode? So discontinuous conduction mode means your current is maybe the zero. Then we can say it is your discontinuous conduction mode. So you can see this time period is a zero. Okay, amplitude is a zero, correct? So we can say it is a discontinuous conduction mode. Okay, so we have a two mode operation, that is a continuous conduction mode and discontinuous conduction mode. Otherwise the circulation conduction mode, otherwise the non-circulation conduction mode. Okay, so that mode that is defined on the current nature. Okay, So for the circulation conduction mode, otherwise the continuous conduction mode, we can say in the circulation control, both the rectifier are controlled together. We have to control the both rectifier together, okay? And how we can control the both rectifier together? By firing angle, correct? We have alpha A for the rectifier A, and we have alpha B for the rectifier B. By controlling the firing angle alpha A and alpha B, we can control both the rectifier, okay? In order to avoid the DC circulation current between the rectifiers, they are operate to produce the same DC voltage across so this is a DC, okay? Same DC voltage across the motor terminal. Thus, we can say the VA plus VB, okay, is equal to 0. Otherwise, we can say the VA is equal to minus VB because both are connected in the anti-parallel. Okay, so suppose one voltage is a positive 200 volt. So second voltage of the second rectifier, that is a minus 200 volt. Correct? Because both are connected in the anti-parallel. Okay. So by substitute from equation number 2, we already studied the three-phase fully controlled rectifier voltage, correct? VA equal to 3 by pi, alpha plus pi by 3, and alpha plus 2 pi by 3, and Vm sine omega t, correct? Vm sine omega t is nothing but Vs. So by using this equation, we already derived the output voltage of the three-phase fully controlled rectifier, that is a 3 by pi Vm cos alpha. Correct? And for the three-phase half rectifier, it is a 3 Vm upon 2 pi 1 plus cos alpha. Correct? So this equation is most important, huh? So that one is used for the numerical solution of the numerical, okay? So you can easily solve the numerical by using this equation, okay? So output of the three-phase fully controlled rectifier, that is nothing but 3 Vm upon pi into cos alpha, and this alpha is nothing but alpha A plus alpha B. Okay, so we can say now we have a two control rectifier. Okay, so we can say 3 upon pi Vm cos alpha. Okay, and alpha is nothing but alpha A plus alpha B. Okay, so we can say the cos alpha A plus cos alpha B is equal to 0. Correct? So we can say cos cancel out, so we can say the alpha A not cancel out, we can say cos 0 is here. Okay, so cos is a common, we can take out the cos is common, then we can say cos alpha A plus alpha B is equal to 180 degree. Okay, so suppose you want to control both the converter, then we have to control the both firing angle of the both rectifier, that is alpha A plus alpha B is equal to 180 degree conduction mode. Okay, otherwise you can say the alpha A is equal to 180 degree minus alpha B. Okay, so this is a simple mathematicals of the operation of the both rectifier. Okay, and both are connected in the parallel with the anti-parallel sign. Yes. Although the control of the firing angle according to relation number 3, and what is the relation number 3? That is a alpha A plus alpha B. Relation 3 is what? So there is a alpha A plus alpha B is equal to 180 degree. Okay. To prevent the DC circulating current, AC does circulate due to the difference between the instantaneous output voltage of the two rectifier. Correct? Because rectifier both are connected in the parallel and there is a voltage difference. Okay. So inductor L1 and L2 are added to reduce the AC circulating current. Okay, so what is the use of the inductor? That both inductors, so there is a reduce the circulating current, correct? So that's why we have to use the both inductor in the dual converter. Because of the flow of the AC circulating current, okay, simultaneous control it's known as the circulating current. Okay, so continuously flow of the current in the circuit, then we can say it is a simultaneous control. Okay, otherwise the continuous conduction mode. Okay, In the three-phase dual converter, inductors are chosen to allow the circulating current of the 30% of the full load current. So this is the most important line. Okay. So how we can select the L1 and L2? Okay. How we can select the L1 and L2? In the three-phase dual converter, inductors are chosen to allow the circulating current of 30% of the full load current. Okay. So we have to consider the L1 and L2 value. It must flow the current that is a 30% of the full load current. Okay. So that much value of the inductor we have to select. Okay. So this completely eliminate the discontinuous conduction. Okay. And therefore give the good speed regulation in the complete range of the drives. Okay. So at least we have to choose the 30% of the full load current. Then you can able to control the good speed response. Okay. Otherwise, maybe the current rating is a low. There is maybe the 20%, yeah, maybe the 10%. Then you are not able to control the good response in the speed. Okay. So we have to control the good speed response in the controlling of the speed of the DC motor. Okay. Yeah. The speed reversal is done as follow. Okay. So now we have a two rectifier. So we can operate in the four quadrant. So how we can do the speed reversal? So we already know alpha A plus alpha B equal to 180 degree. Correct? Is equal to 180 degree. Okay. So by using this relation, we can operate the motor in the reverse direction. Okay. So when operating in the first quadrant, rectifier A will be the 0 to 90 degree, correct? So that is the first quadrant, and rectifier B will be the inverting. Okay. So because both rectifier is antiparallel, so we can say 90 to 180 degree. That is the second rectifier. And suppose you want to do the reverse, so just change this uh, uh, firing angle. Okay. For the speed reversing, alpha A is increased and alpha B is decreasing. Okay. To satisfy this equation is nothing but equation number this one. Equation number 3. Okay. So this is equation number 3. The motor back EMF is exactly the magnitude of VA and VB. Okay. So we already know that alpha A plus alpha B is 180 degree. Okay. That equation is nothing but equation number 3. Correct. The armature current shift to rectifier B, and motor operate in the quadrant 2. Okay. So that is a 0 to 90 degree and 90 degree to 180 degree. Okay. So we can say that is a first quadrant and this is a second quadrant. Okay. First and second quadrant. Okay. Okay. So 0 to 90 degree and 90 to 180 degree. Okay. The current control loop adjusts the firing angle alpha B continuously so as to break the motor at maximum allowable current from initially 0 speed to 0 speed and then accelerate to result the speed in the reverse direction. Okay. So as alpha B is changed, alpha A is also changed to satisfy the equation number 3, and equation number 3 is alpha A plus alpha B is equal to 180 degree. Okay. And the inductance L1 and L2 is increased the weight, volume, cost, and reversal time. The circulating current is increased the losses. Okay. Suddenly drop in the source voltage can cause the large current to flow through the rectifier, working as an inverter and blowing it the thyristor. Okay. So you can see, suppose you want to add this inductor in the circuit. Just a minute. Yeah. Suppose you will add this inductor in the circuit, so this is a disadvantage. So what are the disadvantages of the inductance? So it will increase the weight of the circuit, it will increase the volume, it will increase the cost. So these are the disadvantage of the inductor L1 and L2. Okay. So that's why we can try to replace this inductor L1 and L2 by somehow, so we can reduce the circuit weight, we can reduce the cost of the circuit. And how we can do this? So by, we can say, the discontinuous conduction mode. Okay. So second one, that is a discontinuous conduction mode, otherwise the non-circulating conduction mode. And what is a non-circulating conduction mode? So we can say L1 and L2 not present in the circuit. Suppose both the inductor present in the circuit, then we can say it is a continuous conduction mode. And suppose L1 and L2 are not present in the circuit, then we can say it is a discontinuous conduction mode. And there is an advantage because it is a reduce the size of the circuit. Okay. In the non-circulating conduction mode, otherwise the non-circulating current control method, one rectifier is controlled at a time. Okay. Because now inductor is not there, so we can say only one rectifier we can control at a time. Consequently, no circulating current flow in inductor L1 and L2 are not required. Okay, because there is a no continuously current flow, so it is not required to L1 and L2. So we can reduce the size of the overall circuit, and then we can reduce the cost of the circuit. Okay. This eliminates the losses associated with the circulating current and weight volume associated with the inductor. So these are the advantages of the non-circulation mode. Okay. But then discontinuous conduction occur at the light load, and control is the rather the complex. Okay. So control is a complex. Okay. So there is a non-circulation conduction mode. Then how we can do the speed reversal in the non-circulation conduction mode? When the operating in the quadrant 1, rectifier A will supply the motor and rectifier B will not be operated because L1 and L2 not present. So at a time only one rectifier operate, correct? So at a time only one rectifier is operate. So suppose rectifier A is operate, the rectifier B is not operate. Okay, the firing angle A is set is the highest value. Okay, so we know I alpha A plus alpha B is equal to 180 degree, but alpha B is not operate, so we can say alpha A equal to 180 degree. So we have to try, we can operate our firing angle to maximum value, that is a 180 degree. Okay. Rectifier work as the inverter and force the armature current to zero. After the zero current is sensed and dead time to the 0 to 10 millisecond. Again, this is important. There is a dead time to ensure the turn off all the thyristor of the rectifier A. Okay, so we have a total 6 thyristor. Okay, so we can say it is a turn off. Now firing pulses are withdrawn from the rectifier A and transferred to the rectifier B. Okay, the firing angle alpha B is set initially the highest value. Now we have to turn off the alpha A that is a 0 and alpha B that is a maybe the 180 degree. Okay, to operate the second rectifier. Now onwards, the current control loop adjusts the firing angle alpha B continuously so as to the break the motor at maximum allowable current from the initial speed. Okay. The dead time and therefore the reversal time can reduce by employing the method that can sense the current 0. Okay. So by controlling the one by one rectifier, we can reverse the speed of the motor. Okay, but at a time we have to control the one rectifier because this is a discontinuous conduction mode. Okay. Yes. So till now we discussed the rectifier circuit. There is a single phase and three phase half control as well as the fully control, and also we discussed the dual control rectifier. Okay, so we already know, suppose we have a circuit and that is a advantage and disadvantage, correct? Suppose we have any circuit, so that is a not 100% correct, maybe the 10% disadvantage and 90% disadvantage, correct? So every circuit have a drawback, correct? So drawbacks of the rectifiers with DC drives. Okay, so what are the drawbacks? Okay, so first drawback, that is a distortion of the supply. Yes, because of the rectifier, we have to convert AC into DC. So that is a distortion supply. We can say the THD, we can say the ripple. Okay, the source current of the rectifier is the harmonics. Yes, because of the rectifier circuit. In the weak AC source with high internal impedance, current harmonics distortion of the source voltage. Okay. Maybe I will ask this question in the exam. So write the drawback of the rectifier with the DC drives. Okay. So first one, there is a distortion of the supply. So there is nothing but your harmonics. Okay. Furthermore, temporary short circuit of lines during the computation, not computation, computation of the thyristor, okay, cause shaft current, okay, shaft current, which further distort the source voltage, okay. Source voltage and current distortion have several undesirable effects, including the interference with the other load. So we can say the electromagnetic interface connected to the source and radio frequency interference. Okay, so that is a communication devices. Okay. Second one, that is a lower power factor. Okay, so second drawback, there is a lower power factor. Okay, because of the harmonics, obvious in the first disadvantage, there is a harmonics. Obvious in the system is harmonics is there is a efficiency is very less, correct? So second disadvantage, that is a lower power factor. Okay, so we already know power factor is what? So that is a real power upon the apparent power. And most of the students working in the power plant, correct? So they know very well what is the real power, what is the apparent power, and what is a we can say the apparent power, real power, and what is the third power? What is the name of the third power?
Reactive.
Yes. So real power, apparent power, and reactive power, correct? So we have a three type of power. One is the real power, another one is the reactive power, and third one is apparent power. And which power we can use as a load? Yes, is a लोड कौन सा पावर यूज करता है? देयर इज अ रियल पावर, अपरेंट पावर या रिएक्टिव पावर? Yes, any idea, Isa? So suppose
Sir.
you have a
Sir.
motor. So this motor is consume what power? That is a real power, P.
Yes, sir.
So we can say watt, VA, yeah, VAR. So we can say active power, reactive power, and apparent power.
Real power, sir.
Real power. Okay. Yes, Asut, Madhusudan. Any idea?
That's a real power.
Yeah. So any load that is consume the real power, correct? So power factor, we can say that is a real power upon ratio of the real power to the apparent power, correct? So real power is nothing but the VI cos theta, okay? Upon apparent power, there is a VI, okay? So where V is the voltage, I is the current, phi is your a phase difference between the voltage and current. So we can say this is a voltage and this is a current. So this angle is nothing but your phi, correct? So therefore we can say the PF, that is I1 upon I RMS cos phi 1. So there is nothing but mu cos phi 1. Okay. So there is a low power factor. Okay. There is another drawback of the rectifier circuit. Okay. Where mu is called by the cold distortion factor and cos phi is the phase displacement. Okay. The distortion in the source current make mu is lower than the 1. Okay. So we can say the power factor value is always unity. We can try to make the unity power factor. Okay. But practically that is not possible. Similar here we can say the distortion in the source current, we have to put the mu that is lower than 1. Okay. When motor current is assumed to be the perfect DC source, okay, DC supply, then we can say the phi 1 has the value of alpha for fully controlled single phase and 3-phase rectifier, and alpha by 2 for the single phase half. Okay. For the single phase as well as the 3-phase, that we can say the what we can say the mu value, that is a alpha. Okay. For the single phase fully, so we can say the single phase fully. Single phase fully. Okay. So we can say mu value, that is a alpha. Okay. And single phase half, 3-phase half, mu value is what? Alpha by 2. Okay. Therefore, supply power factor is low when drive operated at the low speed. Okay. So there is a disadvantage. Okay. Yeah, pulse width modulation, we can use the semiconductor. So there is a different type of semiconductor. This is a IGBT, otherwise the GTO, that is a gate type of thyristor. Okay. Sorry. So we can use the different type of semiconductor switches. Third one and most important drawback, that is a ripple in the motor. Okay. Yes, in the first one there is a harmonics, then ultimately reduce the efficiency, and ultimately that efficiency that depend on the your ripple. Correct. The rectifier output voltage is not perfect DC, but consists of the harmonics addition to the DC component. Correct. So we can say the output of the DC is what? Maybe like this. Okay. Not like this. Okay. So this is a pure DC. We can say the pure DC, and this is a distorted DC. Okay. Therefore, motor current also has the harmonics in addition to DC component. So you can see the additional DC component harmonics are there. The presence of the harmonics make RMS and peak value of the motor current higher than the average value. There is a DC components. Okay. Since flux is a constant, torque is a contributed only on the average value of the current. The harmonics produce the fluctuating torque and average value, which is a 0. Okay. So obvious that is a DC. We cannot get in the pure DC from the rectifier. Okay. So there is a ripple in the motor current also is there. Okay. Yeah. So we have a total 3 disadvantage of the rectifier feed DC motor. First one is a distortion power supply. Second one is a low power factor. And third one, that is a ripple in the motor current. Okay. So these are the drawbacks. So that's why we have to work out on the another technology. And that technology name is a chopper feed DC drive. Okay. That is a chopper feed DC drive. Okay. And chopper is what? Chopper is nothing but DC to DC converter. Okay. Chopper is nothing but DC to DC converter. Okay. Yeah. Now I will take only 5 to 10 minutes. Okay. Then we will wind up the class. Okay. So chopper is nothing but DC to DC converter. Okay, so we can discuss the chopper circuit. Okay, so that chopper circuit, there is a buck converter, boost converter, buck boost converter, and cuck converter. Okay, so output voltage buck converter, that is a V input, output voltage greater than V input, output voltage greater than V input greater than V output. Okay, so there is a in between. Okay, and this is a converter, there is a output voltage. So this is a buck converter and boost converter. Cuck converter is just reverse of the buck boost converter. Okay, so we have a four type of converter, that is a chopper converter. Okay, buck boost, and the cuck converter. Depend on application, we have to use this converter. Okay, so first try to understand this circuit. So we can say this is a input voltage V input, then this is a switch. Okay, then this is your freewheeling, not freewheeling diode, so this is the diode. Okay, so we can say the freewheeling diode, okay, to circulate the current. Once the switch is open, then total current is circulate from this freewheeling diode. Okay, and this is your motor. Okay, so this is a simple your circuit of the we can say the circuit diagram of the chopper control of the separately excited DC motor. Okay, so this is nothing but your buck converter. Okay, so here we have to control the only firing angle of the thyristor. Okay, so we have to just control this thyristor. By controlling this thyristor, we have to control this voltage. Okay, because this voltage VA is also depend on this thyristor pulses. Okay, the waveform of terminal voltage, that VA, and armature current IA for the
Excuse me,
continuous
sir.
conduction mode are shown in figure 2.
Excuse me,
yes,
sir.
yeah.
Why the switch is placed in the negative polarity of voltage source?
You can put in the top one also, no issue.
Okay, sir. Sure.
So you can make this one also, no issue. Okay, so that is a just we can say the this is a normal diagram of the buck converter, and this is little bit difficult. So you can put the switch is maybe the top one, yeah, maybe the bottom one. Okay, but we have to make sure there is a switch, one time switch is operate and another time switch is close. Okay, yeah, so we have to analysis the voltage waveform as well as the, so voltage waveform means armature voltage waveform as well as the armature current waveform. Okay, so during the on time period, so we can say this is a on time period, this is a off time period, correct? So we can say yes, switch is on, so voltage is there. Okay, maybe this voltage is a 10 volt. Okay, corresponding current is rise, correct, because we have an inductor and we have resistor. Okay, so current is rise from the some value, that is IA1. Why not from the 0? Because of the battery as well as the inductor. Okay, because inductor is store and battery have some energy, so we cannot start from the 0. Okay, so we cannot start from the 0, but we have some value of the current, so that value may be the 1 milliamp. Okay, and here maybe the 2 milliamp. Okay, so that inductor current is rise, and then is off switch, then that current is decreasing, and this is a continuous conduction mode, correct? So this is a continuous conduction mode. Okay, so current is not reached to 0 again is increasing, and then decreasing, again is increasing. Okay, so on and off. Okay, so this is a simple operation of the buck converter. Okay, we already studied the buck converter in the first semester, otherwise there may be the BTech BTech time period, correct? But I am sure you already studied in the first semester, that is a power electronics. Okay, so we can say the time period T is equal to nothing but 1 by F. Okay, so we can say once the switch is operate, so current is flowing to the inductor circuit, correct? So once the switch is operate, so we can say current is flowing something like that. Okay, otherwise you can say current is flowing from 3 to here. Okay, so we can write the KVL equation RAIA plus LDI by dt plus E is equal to V. Okay, so time period is 0 to T on. That is equation number 1, simple equation, correct? So because we have operate the switch, so current is flow from positive to negative direction, correct? In this interval, the armature current increase from IA1 to IA2. We already seen in the waveform, correct? Armature current is slowly increasing, and IA1 to IA2. Since motor is connected to the source during this interval, it is called the duty interval. Okay. So this time period is called the duty interval, 0 to T on time period. It is nothing but the duty interval. And now that is a off time duration. So now you can see this is a on time period, and now it is off time period. T equal to T on and TR is turned off. Now we have to turn off our switch, correct? So motor current is free wheel to the diode DF. Now we can turn off the switch. Okay, so now we have to turn off the switch from here to here. Okay, so remaining current is flow from this freewheeling diode. Okay. Okay, and that time period is a T on to T. Okay, so motor operation during this interval is known as a free wheel interval, that is described by RAIA plus LDI by dt plus E is equal to 0, because now voltage is a 0. Okay, and duty interval, that is a T on to T. Okay, so motor current is decreasing from IA2 to IA1. So we already seen. So this is a on time period and this is a off time period. So current is increasing and current is decreasing. Okay, on and off. Okay, so maybe current is IA1 and here is a IA2. Okay, so motor current is decreasing from IA2 to IA1 during this interval, and this interval is nothing but your freewheeling interval. Okay, so this is simple definition. Duty cycle is nothing but del is nothing but duty interval divided by T. Okay, so duty interval is what? That is a T on divided by T. Okay, that is a simple duty ratio, otherwise duty cycle del. Okay, then VA, that is a, we can take the one integration, one cycle. So we can say the 1 by T, 0 to T on V to dt. So we can say VA is equal to nothing but del into V. Okay, and V is nothing but input voltage. So we can say V output is what? That is a duty cycle into V input. Okay, and that is the output of your buck converter. So we can write simple, that is a IA, that is a del V minus E upon RA. From that equation, V equal to RAIA plus LDIA by dt plus E. Correct? From this equation, we can write IA. Correct? And also we can write in the form of the speed. Omega m, that is a del V by K minus RA into K square into T. Correct? So this equation number 1, yes, equation number 1, when switch is operate. Equation number 2, when switch is closed and current is flowing from the freewheeling diode. Equation number 3, there is a duty cycle. Otherwise, the duty ratio is nothing but duty interval. That is a T on time period divided by T. Okay. And how much voltage we will get from the buck converter? There is a V output equal to V input into duty cycle. That is a del, correct? And then we can calculate the current as well as the speed from the fundamental drives equation. Okay. Yeah. So yes. So key point from the today's class. So we discussed the 3-phase half control rectifier. We discussed the DC motor reverse and switch diagram, how we can reverse the speed of the motor. Then dual converter. What is a dual converter and how we can operate the dual converter? That is alpha A plus alpha B equal to 180 degree. And drawbacks of the rectifier, we have 3 drawbacks. Okay. 1, 2, and 3. Okay. That is the harmonics, efficiency, and the power factor. Okay. And chopper control separately excited DC motor. That is a buck converter. Okay. So in the next class, we can continue with the regenerative braking. Okay. So there is a regenerative braking. That is a chopper feed DC motor. Speed control of the 3-phase. Speed control of the 3-phase induction motor. And then we will discuss also boost converter. Okay. So we will discuss in the next class. So most probability we will take the 3 more classes for the 3rd unit. Okay. So I think we will complete the 3rd unit after the 3 classes. Okay. So thank you so much. If you have any query, then please let me know. Yes, student. If you have any query, then please let me know. Otherwise, we can wind up this class. Yeah. Okay. If no query, then thank you so much. Yeah. So thank you so much, student, and good night.